big ring, and this is where the majority of Earth's volcanoes are, the Ring of Fire. And we're actually on the Ring of Fire. So you think, well, Kelowna, there's no volcanoes near us. Yeah, there's a few, a little bit closer to the coast, but we're going to talk about those here in a second. So what happens in a hotspot is you get magma rising up through a really strong plume of magma. And we talk about the Mid-Atlantic Rift here is a really big plume that kind of rises up for a really long distance. A hotspot is a really isolated area where magma rises up and it tries to break through the surface. And every once in a while, it does break through the surface. So here's how sort of Hawaii was formed. Get out of the way here. There's a big hotspot underneath Hawaii, and this plate is kind of sliding along. So these islands are being formed as the plate, you can see the direction here, this plate's kind of sliding along the hotspot. So if we can go down a little bit there, Mr. Ross, below. Thank you. Here's an example. I know this isn't like Russian or something, but it's a good example. So these islands over here, about 5.6 million years, 4.9, 3.4. So Oahu is kind of where the capital and everything is. Molokai, Maui, Hawaii. And the most recent one here is Lohi, which is the next Hawaiian island that's forming right now. Soon it'll break the surface and you'll have the next Hawaiian island forming. So this is kind of the most counterintuitive idea there is. The biggest Hawaiian island is Hawaii, and then they generally get smaller as you get older. So I'll ask you this question. If the biggest island is the youngest, why are the Hawaiian islands getting smaller as you move away from that hotspot? Why isn't the oldest island the biggest? If the new island of Hawaii is still being formed right now, why is it's getting bigger? Why aren't the older islands bigger? Does it make sense that the oldest island would actually be the smallest? They're not actually technically going underwater, though the sea level isn't really, well, I mean, it is rising a little bit, but it's not enough. But you're on the right track. It has to do with water. So Hawaii is the biggest, but it's also the youngest. And then soon, Lohi will break the surface and it'll be the youngest, and it'll get bigger and bigger and bigger. Why are the older islands, why are they smaller? What do we think? Has to do with water? That was a good hint, I thought. I thought that was a great hint. The hotspot's stationary, the plate's kind of moving across it. So as the hotspot rises up, it kind of breaks through, makes an island. The island gets formed, and then it breaks through again. Hawaii is still growing. That's why it is the biggest. But why is the oldest the smallest? Come on, somebody's got to put it together. Nobody? All right, I'll give you guys a second. I'm not going to give it up that easy. Let's look at Google Earth. I love Google Earth. Let's look at Hawaii from space, shall we? All right, I'll just stop it there. So you can see this plate's moving this direction, and maybe I shouldn't put Hawaii directly behind my head here. So this is the island of Hawaii, and then Oahu down here, and then Lohi's starting to form right here. You can see this chain. Why are these aren't above the surface anymore? Why are they under the water? This chain, you can see the hot spot kind of moves along here. You can clearly see from space that there's all these islands. Why are these ones underwater now? Why are they no longer above water? Come on, somebody, anybody. Nobody? Am I gonna have to just give you the answer? I feel like I'm cheating you guys if I have to just tell you what it is. I've actually seen this question on provincial exams before as well, so it's an important idea. The water overtook them. You're there, I think you know what you're talking about, but that's not exactly what I'm hoping for. The idea is that the older, remember when we talk about an island being formed, like Hawaii, if I jump around here a little bit, we're talking that this Hawaiian island that where you can go right now is 700,000 years-ish old. If we go back here, we're talking Oahu's 3.4 million, and then Kauai is 4.9 to 5.6. We talk about these really immense time frames. What happens to rock over millions of years? Well, if you're in the middle of an ocean, you have waves crashing on your shore constantly. You have constant rain pouring down. So the older the island, the more erosion that's occurred. Because you have erosion happening for millions of years, the islands that used to break through the surface, they were there, they were big islands. And then the waves break them down, they get smaller and smaller and smaller until they go under the surface. So the biggest island is the youngest because it hasn't had very long to erode yet. It is currently being built. The magma rises to the surface, becomes lava, forms the island, it gets bigger and bigger and bigger. And then that plate moves over a little bit, and then you get the next breakthrough occurs, and that's slowly moving, and it's going to get eroded, and then the new island gets formed, and then you end up with erosion happening over millions of years. So that's a really cool example of a hotspot that's underwater, in the middle of that Pacific plate. Let's look at a hotspot that happens under the ground. This is called Craters of the Moon National Park. It's in Idaho. Has anyone ever been here before? I'll just pause this for a second. Anyone been to Idaho before? Here's Idaho. Here we are up here in the Okanagan Valley. There's Kelowna. And then we jump down into Idaho here. No one's been to Idaho before? Mr. Ross has been to Idaho. Have you been to Craters of the Moon National Park before, Mr. Ross? No. All right. I was lucky enough, my wife and I drove out to Ontario a few years ago, and we went through the States and we went down through here. It was a really cool trip. My mom had actually been to this place before me, and she said, you got to go here. It's a really cool spot. So this is Idaho. It's kind of, yeah, it's a lot of power to wield. You're right, Alex. This is the middle of Idaho, and you can see there's some mountains up here, and then it's kind of like a plains sort of area. And you can see this kind of stain on the surface here of Idaho. And if I go a little bit closer, it's black, which is kind of weird. There's not really much happening. There's no volcanoes to speak of here. But if you go in even closer, and you can see there's another spot down below here, this is called Craters of the Moon National Park. It's in Idaho. And these are all really big lava fields. You can kind of see it in the image here. These huge fields of lava, absolutely huge distances. I mean, hundreds of kilometers. You can see it looks like another sort of, I don't know, planet, I guess. There's these cool tunnels, and I'm going to just zoom in a little bit closer here, see if I can get some other pictures for you guys. Pictures aren't loading. No, don't want that one. Don't want that one. Yeah, I guess that's as good as we're going to get. Anyways, it is lava fields, and it looks like a moonscape. There's absolutely nothing there. There's sort of, you can see the lava. This is what we call primary succession, kind of trying to take over again. But you end up with these immense fields of lava. They're all dried up. This is where you can actually go out, and there's some mountains, like old cinder cones that you can climb, and some really cool stuff. You can see it's lava, like lava that's dried, all over the place. So if I just zoom out, obviously there is some sort of a hotspot that was there at one time. And you can see this big lava field. I mean, this is most of Idaho, and it's a really cool spot if you ever get a chance to go there. But Mr. Borden, what are you going on about? Well, the hotspot used to exist under here, but it's not there anymore because that plate's moving. So can anyone think of an area that's close to Idaho where a hotspot might be significant? If I take a little trip here, does anybody know what this area is called right here? Anybody been to Yellowstone National Park? Now, most students know about this because there's kind of a couple famous Hollywood movies about it, about Yellowstone. Do you think the government hides their secret bases from Google? I have no idea. I'm not kind of skeptical of that sort of thing. So anyways, if you've ever heard of Yellowstone National Park, it is a significant place because there's really cool stuff happening at Yellowstone. Have you ever heard of Old Faithful? It's a geyser that kind of sprays water every, I forget what it is, it's like every hour and a half or something like that. It's a seismically active area. So the hotspot that used to be under Idaho is still there, but now the plate is moved and it's under Yellowstone. So if you ever get a chance to go to Yellowstone National Park, you should definitely go. See if I can find some cool stuff here in Yellowstone. Let's see if I can find a... So you can see like this geyser. Basically the water sort of goes under the ground and it gets heated up and kind of gets blasted out. You can see these bison here with steam rising in the background. It's a really, really cool place. There's lots of really cool... documentaries about Yellowstone. It's so seismically active. There's all these hot springs and things. It has its own sort of unique ecosystem. There's some other pretty cool. You can see all the steam rising up when it gets cold out. Really cool sort of pools that are so hot that you can't go in them. You just die. Geysers, all sorts of really cool stuff happening in Yellowstone National Park. So there is a hotspot. If I zoom out a little bit, the hotspot that's under Yellowstone, it's called the caldera, and it's about this big. So it takes up a corner of the state here of Wyoming, and it's a pretty interesting place. The reason I bring it up, has anyone seen the movie that I'm referring to? I can't even remember what it's called. Is it like the where Yellowstone supervolcano erupts? Why can't I think of the movie name? I'm usually good with movie names. Anyways, the plates all fall apart. I don't think it's the day after tomorrow. They go on the ship, and anyways, that's a movie if you guys have seen it. So this is a map that measures the gravitational field of Earth's surface, and you can see Yellowstone is right here. So normally this should just be kind of greeny blue, but this Yellowstone is pushing up. So there's this super hot spot underneath Yellowstone, and it's pushing up, and basically it doesn't have anywhere to go. It's kind of a really thick continental crust that it's trying to break its way through. Now it gets close to the surface, but there's no magma that's broken through and kind of flowed out, kind of like Idaho, the craters of the moon that I showed you. So it's basically what they call a super volcano, and eventually it will likely erupt, and it is going to be somewhat devastating. There's millions of people that live near it. It'll be a very big explosion when it goes. It's not likely to sort of break through slowly and create a volcano or anything like that. So the map behind me here is shows a map of where the actual caldera is. Old Faithful's a famous geyser. You get some small earthquakes because it's pushing up. 1959, 7.5. 75 at 6.1. So we're talking about some pretty big earthquakes. It's kind of under the Yellowstone Lake. It's a pretty cool place. So there's a hot spot under there. It will erupt soon. We don't know when, but it's likely to happen in the next few thousand years. Might be here, we might not. You never know. But usually students ask lots of questions about it because of the movie that I can't think of the name of, though. Yeah, I know. They can happen in our lifetime, and they can happen not in our lifetime. It's just the time scale is so large when we talk about these geological processes. Seismic waves. We talked a little bit about how we know so much about the center of the Earth, but we've never been there. So this is some of the evidence that we use to kind of make up the ideas of what the core of our Earth is going to look like. So seismology is the study of seismic waves, and these are the waves that are released when earthquakes happen. And you can see here they help us learn about the composition and substances of Earth's interior. So if we have an earthquake happening, the epicenter is the point on the surface where it happens. There's basically two types of waves that an earthquake releases. P waves are called primary waves and S waves are called secondary waves. Now, they travel at different speeds and they can go through different substances because they're different types of waves. So we look at the image here, we know that the outer core of the Earth is liquid because the P waves that would normally travel, the S waves that would normally travel through get blocked by it. We know S waves can't travel through liquid. So we know the outer core of our Earth is liquid because when an earthquake happens, you end up with these areas on the far side of the Earth that these S waves don't make it to. So you end up with this big sort of shadow zone. And then we can look at how the P waves bend when they enter the solid inner core. And we can use like computer models and we can figure out exactly where those lines will end up on the far side of the Earth based on it going through a solid core. So this is how we know about the interior of our Earth, because you end up with these waves that get transferred through it. So the image above me here, I know it wasn't Star Trek. I'll look it up. I'll tell you tomorrow. I'm going to feel silly once I look it up. These are earthquakes seismograph readings. So this line here is really flat, and then you get this small shaking. This is a P wave, or the primary wave, and then you get this big jump, which is the secondary wave, and then you get the earthquake, which actually happens, which is some other waves, L waves and things like that. So when you see an earthquake happening, if you can tell the difference between the first P wave hitting and then the secondary or S wave, you can figure out how far away the earthquake is. And if you can use 3 stations, you can figure out exactly where the focus of the earthquake was. So we're actually going to do that next day. We won't have time today. We'll just get as far as we can through this stuff, and then we'll actually do the demo, the earthquake lab together next day. We'll do it together in class. So you need to know the types of earthquake waves. The first one's P wave, primary wave. The second one is an S wave, a secondary wave. Those ones make sense. And then the third one is L waves, or surface waves. And these were actually named after scientists, and their L waves are love waves because his last name was Love. So that's why they're called L waves. So the P wave's kind of like a small shaking, and then an S wave's like a bigger shaking, and then the L wave is kind of like the rolling that causes all of the damage. And we'll look at a few videos and things like that. So I don't know if you've probably experienced this. If you were to go outside, maybe you've seen fireworks happen before, and the first one goes up, and then you see this bright flash of light, and then you hear the big boom afterwards, or lightning storms. Have you ever counted in a lightning storm? Was it supervolcano? It could have been. In a lightning storm, you see a flash of light, and then you count 1 Mississippi, 2, to figure out how far away the lightning bolt was to your house or where you're standing. That's the same idea as with earthquakes between the primary wave and the secondary wave. If we can figure out exactly the distance between those things, we can figure out how far it was away from that point. And we can use something called triangulation to figure out exactly where it happened. So that's what we do. That's how we study. That's how we find out where earthquakes epicenters were, between, the distance between the P wave and the S wave. All right, so these are the 3 types of waves. P wave's primary wave, and it is a compressional wave. It goes like this, and sound is a compressional wave as well, so P waves and sound waves are very similar. And then you have your secondary wave, which is a transverse wave. Now, the easiest way to talk about transverse waves is if you've ever been to a stadium before, and people in the audience do the wave where it goes around, and then it comes back to you, and you stand up and you do the wave. That's a great example of a transverse wave. Now, the reason a transverse wave is special is because if you think about when I am in a stadium and I stand up and do the wave, I raise my arms up. But which way is the wave traveling? The wave's traveling around the stadium. It gets back to me, I raise my arms up. So my motion is up, but the wave's actually traveling past me. So that's a good way to think of a transverse wave. So compressional waves go in and out. Transverse waves go up and down, but they're actually traveling that direction or that direction, which doesn't make sense. And then you have the L wave, which is a surface wave, which is this rolling that you end up with. And the L wave is the one that causes the most damage. Now, Taylor, you'd mentioned that there was an earthquake in the lower mainland not too long ago, which you felt, and they do happen from time to time. I've only experienced sort of one earthquake that I can recall that was strong enough for me to notice. And it happened when I was in high school, so I would have been in grade 11. And I was at the old Kelowna Secondary School on Richter before it burnt down and they tore it down. It's kind of on the corner of Richter and the highway. And I was on the second floor, and underneath was kind of like place to lock up your bikes. So there's kind of pillars that we were kind of up in the air above. Anyways, we're sitting there in social studies class, which was kind of cool. And we had an overhead projector with a screen, and the screen started to rattle. That was the P wave coming. It was like, and we're like, whoa, that's really weird. And I kid you not, the P wave happened, the earthquake happened in Seattle, so it was a long ways away from us, but we still felt it. I looked outside of the window, and as I was looking out, I was looking towards Knox Mountain, so you can imagine looking at Knox Mountain. Now, the P wave hit, the shaking, and the S wave came next, which was just more shaking. And then when that L wave came, was like a rolling of the surface, I could look out of the window and I saw Knox Mountain, and then I didn't see Knox Mountain, and then I saw Knox Mountain, and then I didn't see Knox Mountain. And the whole building was just rolling on these L waves. And it was like being on a boat where you can see the horizon, and then it kind of goes out of view, and then you can't see it, and then you can see it. And it was a really kind of surreal experience. Made my stomach really upset, kind of like feeling like on a roller coaster. And it was just kind of really weird. Now, it wasn't a strong earthquake, but we were just close enough that we could feel it. And it was a weird feeling. So if you've ever had a chance to experience something like that, it's kind of scary. Hopefully you're not close to the epicenter, but you end up with, the actual ground will roll. That is the amount of energy we're talking about here in earthquakes. Just regular ground rolls. We can't fathom how much energy is in these things. So P wave primary, S wave secondary, L wave is the love wave, or kind of the rolling waves. We'll watch these two videos and then we will call her a day. So this is just showing the difference between the waves. Let's see if we can get into this without an advertisement.
Longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
All right, so pretty basic explanation of the two types of waves. Compressional wave goes in and out. Transverse wave, I go up, the wave goes along and then comes back. There you go. This one I love because people that don't understand science think they come up with these crazy kind of theories and things like that. And this is a beautiful example of it. So people say, oh, animals can sense an earthquake before it happens. And fair enough, maybe they can. But I'm going to kind of try to argue against that. So if you watch this video, it's a dog before an earthquake happens. Here's the dog here. And then you see the dog take off. And then the guy behind this post says, what's going on, dog? And then an earthquake happens. So somebody who doesn't really know a lot about science would say, hey, that dog sensed the earthquake before it came. I mean, it wasn't a long time before it happened, but he did sense it. So you see the dog sitting there, looks at the ground, and then he takes off. And then the guy's like, where are you going, dog? Come back. And then boom, earthquake. All right. Remember how I told you that the P wave, the primary wave, is a compressional wave. It goes like this. It also happens that sound is a compressional wave as well. So what is actually happening here is dogs have different abilities to hear different frequencies than we do. As that compressional wave was moving through the ground, it actually entered the atmosphere and became a sound wave. So if you watch the dog really closely, you'll notice the dog tilts its head a little bit and looks at the ground. So he can actually, exactly like a dog whistle, same deal. The dog hears the earthquake right there because it's coming. The wave traveling a little bit faster in the air, and then you get the actual earthquake happening. So when people say, oh, animals can sense earthquakes before they come, well, I guess we could sense a sound. That's one of my senses. They just heard it. That's all they did. I mean, there's probably evidence to say that they can actually physically sense them or whatever. I don't know, that they have some magical sixth sense. But it actually is likely just the dog hearing or an animal hearing the wave before it came. So again, if we talk about the waves that are happening here, this video is a bit difficult, but if you watch it, it's always pretty standard. You can see everything start shaking, and then it stops, and then there's the S wave happening, and then you get some serious shaking happening. So you get the P wave, you get a little bit of vibration, and then it kind of dies for a second, and then you get the big S wave, and then the L wave kicks in, and everything starts going crazy. Any earthquake video you ever watch, they'll always play out the same way, where you have everything just kind of vibrates. That's, letting people know that the earthquake's going to happen, and then you get the big S wave and the L wave, where everything kind of just falls apart. And it's pretty cool. There's literally thousands and thousands of videos online, CTV or CCTV, like security cameras and things that film earthquakes. But if you watch them, you can watch for the P wave to come. You can watch for the S wave to come, and then everything just lets go once that S wave and L wave comes. And they always happen the same way. The closer you are to the epicenter, the less distinction there's going to be between the P and the S and the L. The further you are away, it's very distinct. You have the primary wave, just some rattling, and then you get the S wave where things start to shake really big, and then the L wave, things just kind of fall apart. Really big earthquakes will happen for minutes, not seconds. So Taylor, you're talking about the one that you experienced was like 5 seconds. That's really short. If you were in Japan when that big one happened, the ground shook, like really shook for minutes. And then you get aftershocks, which do the same thing again and again after the initial earthquakes happened. That the plates will, if you have a subduction, the plates will slide, and then it gets stuck again, and then the energy builds, and then slides again, and slides again, slides again, slides again, until it kind of falls into place. So earthquakes are really devastating and very powerful. And we're going to talk about seismometers. We're going to talk about that earthquake lab that is mentioned in the learning guide. There's actual assignment. We'll talk about that all next day. We'll go through it together as a class and make sure everybody's on track with that. So I'm going to leave you guys there. You should be able to get as much done in the learning guide as you can. If you haven't finished 1 through 3 units, get those done before the break. I'll put a due date of Friday for Unit 10. Hopefully you can get it done by then. If you can't, I'll give you the break, but you should be done Unit 1, 2, and 3 before the break, Unit 10 by the end of the break. So we're starting on chemistry after the break, and you don't want to be doing this stuff while we're in the chemistry unit, because chemistry is tricky. I don't think there's a ton of pages left in that learning guide, Abby, in terms of notes. We'll talk about seismographs, we'll talk a bit about volcanoes all next day, and then we'll go through that lab together. So you could probably do most of it in the learning guide. I don't think there's anything in there that's terribly difficult, but just use your best judgment for that. Hopefully you can finish that by Friday. That's the goal. This is the only unit in earth science. We might have time, Anna, at the end of the year. If we haven't run out of time, there's a couple other units. There is a unit on radiation, which is kind of related to earth science. And there's a couple units on weather and energy transfer in the atmosphere. We might not get to them. We might get to them. I'm not sure. So this is kind of it for earth science for now. What would the dog hear? Yeah, you said that. I'm not sure what frequency the wave would kind of transmit at, if it'd be really low or really high. I have no idea. You could maybe look it up. I don't know if there's any research that's been done on that. I'm sure there probably is, but I'm not sure what the dog would hear. But it would be like a constant noise for a couple seconds, and then boom, earthquake. So we'll leave it there. I won't see you guys tomorrow, but I will see you on Wednesday. I think there's something going on at the museum today. I saw on the calendar. So if you're going down to the museum, that would be awesome. I have class, so I won't be there. But it'd be cool if you could come down and check it out with Mrs. Ward and Wood. And we'll see you guys on Wednesday. Have a good afternoon.